In the 1930s, scientists Enrico Fermi and his colleagues in Rome, and Otto Hahn, Lise Meitner, and Fritz Strassmann in Germany tried to produce new transuranium elements by bombarding uranium-235 with neutrons. To their surprise, they found that rather than fusion, they obtained nuclear fission, fragmentation of large nuclei into smaller pieces, which is what you can see here. So in this section, we're going to describe the processes of nuclear fission and fusion. So in nuclear fission, a large nucleus is bombarded with a small particle. The nucleus splits into smaller nuclei and several neutrons, releasing large amounts of energy called atomic energy. This energy is the most important product of this decay reaction. And it is produced because the products have less mass than the starting nucleus. When a neutron bombards uranium-235, an unstable uranium-236 undergoes fission. Smaller nuclei are produced, such as krypton-91 and barium-142. In addition, the neutrons emitted have high energy and can bombard unreacted uranium-235 nuclei. So here this depicts a typical reaction for nuclear fission. You can see that we have to have a balanced equation. We're bombarding with one neutron, we get a larger uranium nucleus which is going to undergo fission. And you can see there are 3 neutrons that are released that then can go back and react, and we have this release of energy. So I said to you before that energy released is the most important product. We have to release that energy because what we will see is that the total mass, right, is slightly less than the mass of the starting materials. And Einstein confirmed that this missing mass is being converted to energy because we can neither create nor destroy mass or energy when we undergo a chemical reaction. That's that conservation of mass and energy in a reaction. So neither can be created or destroyed, so it has to be conserved. So this missing mass is converted into an enormous amount of energy consistent with Einstein's famous equation, E equals mc squared. This conservation of mass and energy, this is the first law of thermodynamics, which again we haven't learned yet, but you just need to keep it in the back of your mind when we're looking at these reactions. So what happens is with those 3 neutrons that are produced, they can go back and react with unreacted uranium-235. And this is going to produce what's called as a chain reaction, or a self-propagating reaction that is just going to continue as more neutrons are produced, and then they go back and bombard further uranium-235 atoms. If all 3 neutrons are allowed to produce new fission, the rate of the reaction increases constantly and eventually culminates in a nuclear explosion. In nuclear power plants, the rate of reaction is controlled by inserting boron control rods into the reactor to absorb neutrons and dampen the rate of fission. Right. So this is talking about that chain reaction, that self-sustaining or self-propagating reaction. So a critical mass of uranium undergoes fission. You're going to have a rapid increase of high energy neutrons because you release 3 neutrons per reaction. So to sustain this nuclear chain reaction, you need to have sufficient quantities of uranium-235. All right, so now let's look at the other side, nuclear fusion. Nuclear fusion combines small nuclei into larger nuclei. An estimated 98% of all matter in the universe is made up of hydrogen and helium. The Big Bang theory of the formation of the universe postulates that our universe started with an explosion, a Big Bang, in which matter was formed out of energy, and that at the beginning only the lightest element, hydrogen, was in existence. Later, as the universe expanded, stars were born when hydrogen clouds collapsed under gravitational forces. In the cores of these stars, hydrogen nuclei fused to form helium. So if you look, the fusion of two hydrogen nuclei into a helium nucleus liberates a very large amount of energy in the form of photons. Okay, so here we're having the combination of two hydrogen nuclei to form helium. This process is called nuclear fusion. It is how the sun makes energy. Uncontrolled fusion is employed in the hydrogen bomb. If we can ever achieve a controlled version of this fusion reaction, which is unlikely to happen in the near term, we should be able to solve our energy problems. And so just to point out, so here, this is an isotope of hydrogen. It's called tritium. It's where you have an extra neutron. And here we have our conventional hydrogen nucleus with one proton and one neutron. And they'll combine to form helium, a neutron, and photons. And this is the reaction that occurs in the sun and the stars. Fusion reactions have been used to produce all of the trans uranium elements. So here you have heavy nuclei being bombarded with light nuclei. Many of their names indicate where they were first prepared. These reactions require large amounts of energy. Importantly, less waste is produced in a fusion reaction than in a fission reaction. If we could solve this problem of being able to stably combine your hydrogen isotopes to form helium, as I said previously, we would solve our energy problems. When we were looking at chain reactions, I mentioned the use of boron control rods to help slow the rate of a chain reaction. In a nuclear power plant, the energy produced by fission is sent to heat exchangers and used to generate steam. This drives a turbine to produce electricity. Today, such plants supply more than 15% of the electrical energy in the United States. The opposition to nuclear plants is based on safety considerations and the unsolved problems of waste disposal. Although nuclear plants in general have good safety records, accidents such as those at Fukushima, Chernobyl, and 3 Mile Island have caused concern. So you should remember Fukushima was in our lifetime in Japan. So you can see that process depicted here, where you have heat from the nuclear fission reaction and it's used to generate steam, which then is used to generate electricity. Nuclear waste disposal is a long-range problem. The fission products of nuclear reactors are highly radioactive themselves, and they have long half-lives. Spent fuel contains these high-level fission products as nuclear waste, together with uranium and plutonium that can be recovered and reused as mixed oxide fuel. Reprocessing this fuel is costly. However, it is done routinely in Europe and Russia. It is not currently practiced by nuclear plants in the United States for economic reasons. However, this situation may change because cleaner extraction processes have been developed that use supercritical carbon dioxide. Again, we haven't learned about this. You don't have to remember these details. I'm just giving you a little bit of information about nuclear waste. Let's do a learning check. For each of the following, indicate whether it describes nuclear fission or nuclear fusion. Pause your video and answer the questions. So you can see when a nucleus splits, it's fission. Large amounts of energy are released pertain to both fission and fusion. Small nuclei combining to form larger nuclei is fusion. Hydrogen nuclei reacting is also fusion. When several neutrons are released, that is a fission reaction. All right, let's do another learning check. Supply the missing atomic symbol to complete the equation for the following nuclear fission reaction. All right, so pause your video. Remember, whatever's on the left side has to balance what's on the right side. So we have 236 and 92 to balance. All right, so 236 minus 137 minus 2 equals 97. And then 92 minus 52 minus 0 equals 40. So if you look at the element that has an atomic number of 40, you'll see that it is zirconium. This video concludes our discussion of Chapter 5. From the math side of this, you're going to have to be able to look at the half-life. You're going to have to be able to convert between the different units of measuring radioactivity. And you are going to have to balance nuclear equations. The homework that is assigned will be reflective of what you need to know from this chapter.